see who will be eliminated from the race tonight.
No, not that type of elimination, you silly. Linear algebra elimination.
Oh!
But before looking at the cool elimination in the world, we need to understand matrices and vectors. We all know the standard xy plane. We can plot points and lines. Now what about vectors? So adding vectors is really simple. We take each other's first components and then add them, and then their second components and add them, and so on and so forth until we have added every component. Scalar multiplication is also very simple. Every component gets multiplied by the coefficient. Multiplying vectors to other vectors is less intuitive. We use what's called the dot product. We multiply each component and then add the result to get a number. And it's really important to note that vector addition and vector multiplication are associative. Now what if I were to take these two vectors, which only meet at the origin, and take all their linear combinations? This means that I multiply each vector by any scalar and add them to each other. I would get the entire xy plane, but if these vectors are combinations of each other, meaning they are dependent, I would only get a line in R2. Dependence and independence will become really handy for when we perform elimination. We can combine two or more vectors to get a matrix. Matrix addition is the same as vectors, and it's also associative. But it is crucial to note that matrix multiplication is not associative, meaning A times B is not always equal to B times A. Every entry of the product is a dot product of the matrices it is a combination of. So row I, column J of the product is a dot product of row I of A and column J of B. Matrices are just like equations. We can take the left-hand side with the unknowns and put all the coefficients into the matrix. The right-hand side remains vector. We multiply the matrix A by our unknowns to produce our right-hand side B. Just like a system of unknowns in linear algebra, we're trying to solve for x. To do so, we need to eliminate. Using row operations, we can add, subtract, or exchange rows. Take this example. We can subtract 2 times row 1 from row 2. Then we can add row 1 to row 3. Now we have eliminated the first column. Then we can add row 2 to row 3 to reach an upper triangular matrix with what are called pivots in the diagonal positions and zeros below it. We need the zeros below the pivots in order to reach an equation with only one unknown. Always remembering to do the same elimination steps on the right-hand side B too. If any zeros are in the pivot positions, elimination breaks down and there's no answer to the solution. That is because we would either have too many equations and not enough unknowns, meaning that there are an infinite number of answers, or we would have too many unknowns and not enough equations, meaning that there isn't a single answer. But if we reach a nice matrix, then we can perform back substitution to solve for x by plugging the coefficients back into the equation and doing some good old simple algebra. So why does this matter? Elimination and linear algebra are crucial to everyday life. I mean, Netflix, Amazon, and Google use machine learning in their sorting systems, and linear algebra is the foundation of machine learning. Can you imagine life without them? So the next time you're watching The Amazing Race, just ask yourself, does that team have zeros in the pivot positions? If so, then they might get eliminated.